All right, so here's the screencast for thermodynamics. We're going to talk about basically heat and energy in terms of reactions. Some of this we've already covered with endothermic and exothermic reactions, but we're also going to talk about the laws of thermodynamics as well as specific heat. So here are your two essential questions for this presentation. So thermodynamics, it's the study of energy, work, and heat. It is applied to chemical changes. There's usually an energy change, even if it's a slight energy change. There's usually an energy change with every chemical reaction. So you can calculate, the quantity of heat that's obtained from combustions of 1 gallon of fuel oil. That's an example of a thermodynamic problem. It can also be applied to physical changes. Determine the energy released by boiling water, or the energy taken in by water that you are condensing, water vapor that condenses, or water that's freezing. So one thing that you have to remember is the system versus the surroundings. The system is the process under study. That's the actual chemical reaction. So that's either going to be absorbing or releasing heat energy, and what we measure is the surroundings. We see what happens to those surroundings. If something absorbs energy, it gets cold. The surroundings get cold. If something releases energy, so if the system loses energy, then the surroundings get warm. So we measure the change in energy during these chemical changes by looking at what happens to the surroundings. That tells us what happens at the system. So if the system is losing energy, then the surroundings are going to gain it, and that's why the temperature goes up. If the system is gaining energy, then the surroundings are going to lose heat energy and the temperature goes down. So energy can be lost, energy can be gained, but you have to think about it. We're measuring the surroundings, so you have to think about what's happening at the system level. So the first law of thermodynamics, energy in the universe is constant, also called the law of conservation of energy, meaning energy can neither be created nor destroyed, but it can be changed. And so we see this change happening in endothermic and exothermic reactions. So each chemical bond is stored chemical energy. So when you break these bonds, you are releasing chemical energy, and then you are taking in chemical energy to make those bonds. So whether there's a net gain or a net loss, that determines if your reaction is exothermic or endothermic. But if a reaction occurs, bonds are going to break. Breaking bonds requires energy. Then energy is going to be released, and then energy is also going to be used to make those bonds. So these bonds must be broken, so they require energy. These bonds are formed, releasing energy through an exothermic reaction. But we think about the net release. If your net release is your products now have less energy than your reactants did, that's an exothermic reaction. An endothermic reaction is where you have a net gain of energy, where your products have more energy than your reactants did. So that's where we've seen these energy diagrams before. What happens through the process of a reaction? This one is clearly exothermic because you are losing energy. This one is clearly endothermic because you are gaining energy. So in an exothermic reaction, you see energy on the product side, and that would make the temperature rise. In an endothermic reaction, you would see energy on the reactant side, and that would make the temperature lower. So what is enthalpy? Enthalpy is heat energy. So whenever you see this delta H, this change in H, that is enthalpy. Enthalpy is the energy difference between the products and the reactants of a chemical solution. So like back here where we were looking at this is the change in enthalpy, and this is the change in enthalpy. So in here, this one has gained energy, so you have a positive enthalpy. This one has lost energy, so you have a negative enthalpy. So the delta H, or enthalpy, over the course of the reaction can be determined by looking at how much energy the products have minus how much energy the reactants had to begin with. So it can be positive or it can be negative. If it's negative, you gained energy. If it's positive, you lost energy. So if the reaction is exothermic, the sign will be negative. Whoops, I said that backwards. If the reaction is exothermic, the sign of delta H will be negative, meaning the reaction has lost energy to the surroundings. So you are going to have a negative effect on the enthalpy, but it's going to be increase in the heat energy. If the reaction is endothermic, the sign will be positive, meaning it has taken in heat energy and the surroundings are going to feel cold. So are the following processes exothermic or endothermic? Just based on the enthalpy, if it's negative, you know that it's lost energy. If it's positive, you know that it has gained energy. So in endothermic reaction, we see positives. In exothermic reaction, we see negatives. So the second law of thermodynamics, the universe is spontaneously tend towards increasing disorder or randomness. This is called entropy, not to be confused with enthalpy. Enthalpy, think heat, it has an H in it. Entropy is chaos. Think about how easy it is for your room or your house to get messed up, for it to go to chaos, but how much energy you have to put in to get it back in order. That's entropy. So which substance has the greatest entropy? What you're looking at is which has more randomness. It wants to go towards disorder or randomness. So when you compare something that's a gas to a solid, this is more orderly, this is less orderly because the gas particles are moving faster and they have less of an attraction to each other, so this has higher entropy. A liquid versus a gas, the gas is going to have higher entropy because they're not as cohesively stuck to each other, so this one's going to have more chaos to it. So a way to tell entropy is if you have a positive S or a positive change in S, that means an increase in disorder. A negative change in S means a decrease in disorder. So entropy increases, entropy decreases. The second law of thermodynamics, in just a representation, if we're going through the phase changes, going from a solid to a liquid, you're increasing entropy. Going from a liquid to a vapor, you're increasing entropy. Going from, or something dissolving, you're increasing entropy. So all of these would have a positive change in S. So if a reaction is exothermic and it has a positive entropy, that's going to be a spontaneous reaction, meaning it's just going to happen. You don't have to give it a trigger. It's just that reaction is going to happen. If the reaction is endothermic and negative, meaning it has to take in energy from the surroundings and it has a negative entropy, meaning you're putting things back in order, it's non-spontaneous. You're going to have to give it something to get it to go. You are going to have to give it energy to get that reaction to go. So a spontaneous process, diffusion is an example of a spontaneous process. It's going to move from high to low. A non-spontaneous process, one that's going to require energy, is active transport, where you're going to have to try to pump or move something back against its concentration gradient. You're going to try to put it back in order. It doesn't want to do that. It's going to require energy. This will happen spontaneously. This will not. The delta S is negative. So free energy, our last variable here, is delta G. Free energy represents the combined contribution of the enthalpy and the entropy values for a chemical reaction. Free energy predicts the spontaneity of a chemical reaction, so it allows you to determine if it'll go or not. If something is a negative delta G, it's always spontaneous. If it's a positive delta G, it's never spontaneous. So just thinking about if a reaction will go. And here's the equation to calculate delta G. Your delta H minus time delta S, or temperature. So you need to know both delta H and delta S to predict the sign of delta G. So temperature also may determine the direction of spontaneity. So this is just a little bit of analysis of an equation. If the delta H is positive, or if you have a positive delta H and a negative delta S, the delta G is always positive regardless of the temperature. A negative delta H, which is enthalpy, a positive entropy, your delta G is always negative regardless of temperature. If they're both positive, then it depends on temperature. If they're both negative, then it depends on temperature. So these are just some different scenarios on what your entropy and enthalpy values might be to determine if that reaction is going to go. You can experimentally determine how much energy is involved in a chemical reaction by using a by doing calorimetry, using a calorimeter, a calorimeter. Sorry. You guys have done this in biology, so we're actually not going to do it. We're going to do it in a simulated sense. But calorimetry is the measure of heat energy changes in a reaction. So it's a way for you to tell how much energy the water absorbs, and that'll tell you how much energy whatever you had gave off. So the change in temperature of the solution caused by the chemical reaction can be used to calculate the gain or loss of heat energy, which is Q for that reaction. So in an exothermic reaction, heat is released by the reaction, is absorbed by the surrounding solution. In an endothermic reaction, the reactants are going to absorb heat. So exothermic, it gets warmer. Endothermic, it gets cooler. And then here's the equation to calculate specific heat. Specific heat, SH, is the number of calories of heat needed to raise the temperature of 1 gram of the substance by 1 degree Celsius. And so you just plug in all of these values. To determine the specific heat released or absorbed, you need to know what the specific heat of your substance is, the mass of the solution you have in grams, and the temperature change. So this is the mass, this is the temperature change, and then this is the specific heat of the solution that you're working with. So we're going to go through a couple of practice problems, just being able to plug these values into an equation to calculate how much heat energy is going to be absorbed or released. And then you can tell if those reactions are endothermic or exothermic by if they are positive or negative numbers. Positive number would be the reaction is exothermic. So we will go through and work through this example problem together. The Baum calorimeter and measurement of calories in foods. We've talked a little bit about this, but the food calorie, the nutritional calorie, is actually 1,000 small calories. So when you look at the food that you eat and it says it has, 100 calories in it, it actually has 1,000 times that. It means it's telling you kilocalories. So we can use this to measure kilocalories if you're actually trying to figure out how much calories is in the food that you're eating. So calculating the fuel value inside of foods. We're going to go ahead and work through this example problem together. So I'm just going to go ahead and skip through this because we're going to work through this in class. And that concludes our discussion on thermodynamics.